this talk, it can also be just a pseudo-spin, so it can also describe a Dirac semi-metal. So as a result of that, we have this familiar low energy dispersion relation when the energy disperses linearly with the momentum. So in that respect, Weil semi-metals can be thought of as three-dimensional generalizations of graphene. And so if you go to momentum space, you see these two monopole-like hedgehog type of structures in momentum space, which kind of visualize what happens to the Berry curvature around the Weil nodes around these 2 points. Right. So what are the expectations? So let's just take, for simplicity, non-interacting Weil fermion. So this is like a non-interacting Fermi gas with a peculiar dispersion relation. So if you check some textbooks written on NMR, you find that the nuclear spin relaxation rate T1, so that's the time scale during which the nuclear spin relax if you kind of perturb them out of their equilibrium situation, and then T, this is the temperature, so 1 over T1T, this is a dimensionless number practically. So if you check some textbooks, what you find is that this is directly proportional to the square of the hyperfine interaction A and the square of the density of states in the surrounding medium. So whether this is a Weil semi-metal or graphene, I will discuss this in a second. And so there is this energy scale. This is the argument of the density of states. So this is the maximum of the chemical potential or the temperature. So let's see how it comes. Well, let's see what it gives us. So let's just consider a normal metal where the density of states is a constant. So this is a pretty good approximation unless you are very close to the bottom or a top of a conduction band. But if you are somewhere close to the middle of the band in a normal metal, the density of states is a constant. So in that case, 1 over T1T, this is just a constant. It does not depend on either on the chemical potential or on the temperature. So assuming that you know the density of states of your system, you can get some information on the hyperfine coupling. And then this can be important to estimate 1 over T1, so the relaxation time of these nuclear spins, because so one way to use NMR is to get information about the surrounding electrons, but then you can also use these nuclear spins to perform some quantum computation or to build an NMR quantum computer. And then knowing the characteristics of the relaxation, namely the hyperfine and the DOS, these are kind of essential quantities. Now let's consider a more exotic system, namely graphene, when the density of states behaves linearly in energy close to the Dirac point. So in this case, there can be a significant energy dependence. And then for small temperatures, the 1 over T1T scales with mu square, so the chemical potential square, while if you go to very high temperatures, it will scale with the temperature square. So it has not been observed in graphene for several reasons, but there are also some other materials which possess a tilted two-dimensional Dirac cone. And then in those materials, this kind of prediction was nicely observed experimentally. So what do we expect based on this very simple kind of textbook picture on Weil semi-metals? So we know that the density of states in Weil semi-metals change with the square of the energy. So based on that, 1 over T1T should scale with mu squared, so the chemical potential, mu to the fourth power for very small temperatures. So this is kind of analogous to what happens in a normal metal when 1 over T1T is just a constant. So this is just mu to the fourth. While if you crank up the temperature, then 1 over T1T acquires a kind of strange temperature dependence. And so it will diverge, it will grow with temperature to the power of 4. So these are just the naive expectations. But then we thought that maybe we should give a kind of a closer look at this, whether this is still the case or whether we need to modify this very simple textbook type of approach for Weil semi-metals. And then here is a short intro on NMR, nuclear magnetic resonance. So what we do here is that there is a nuclear spin. This is I. This is the spin of the nucleus. And so if there is no magnetic field, let me assume that I is a spin 1/2. So the two spin states are degenerate. If I apply a magnetic field, there will be a splitting. So the magnetic field will introduce a splitting, which will be proportional to a magnetic field. And then if you excite the spin to be in this upper level, then you have the chance to measure this relaxation time T1. So this is the typical time scale the spin spans in this excited state. And so this is not what they measure in NMR, but if you want to think of it in terms of a resonance, this is how the NMR spectroscopy would look like. So that is the position of the resonance. This is the gyromagnetic factor. This is the magnetic field. And so if there is no coupling to the environment, the resonance occurs exactly at gamma dot B. However, if there is coupling to the environment, there is a hyperfine coupling. This resonance gets shifted exactly by this night shift. So this is K here, which tells us about the position of the resonance. And if there is a resonance, there is also a half band, half width, full width at half maximum or something like that. This is 1 over T1. So this is kind of the lifetime of the nuclear spin. This is the broadening of the resonance. And so how do we determine the hyperfine coupling? What's the derivation of that? So at first, one may think that one should start to derive a Heisenberg type of model describing the interaction between the nuclear spins and the conduction electrons. But the nuclear spin is pretty well localized to within the nucleus, so this is not a really good approach. So what we do here instead is that we take the nuclear spin as a classical dipole. So since we have a classical dipole, we can associate a vector potential and also a magnetic field to it. And then the nuclear spin will interact with the conduction electrons through the pair substitution. So we have to make this minimal coupling. So we need to shift P, the momentum, by the vector potential, where this vector potential is kind of represented by that of the dipole of the nuclear spin. And there is also this Zeeman term, the B dot sigma form. So these are the two types of interaction which kick in when you want to derive the hyperfine coupling. So let's just consider a normal matter first. So this is like a 3D parabolic band. So if you do these steps, what I outlined before, and then after some straightforward algebra, you find that the hyperfine coupling has 3 terms. So there is an orbital term, and there are 2 related terms, which are called the spin dipole and the Fermi contact term. So in the case of a normal metal, this first term is the orbital term. So upstairs, you see this R cross P. This is the orbital angular momentum L of the conduction electrons. So I, that's the spin of the nucleus, that's the spin of the nucleus. So it has this I dot L form, and then it is not sensitive to the physical spin of the conduction electron. So this is why this is called an orbital term. And there is also the spin term, which contains the spin dipole and the Fermi contact term. So this is not going to be important here, but this is just a long-range spin dipole interaction between the localized nuclear spin and that of the conduction electrons around the nuclear spin, right? So this is what happens in a normal metal. And now we are going to generalize this to Weyl semimetals. So what we do here is that we take this Weyl Hamiltonian, we do the pair substitution. So we shift P by the vector potential, plus we also add the Zeeman term of the form B dot sigma. So if we do that, this is the hyperfine coupling, what we can derive for Weyl semimetals. So let me try to explain these various terms. So previously, I gave you the expression in real space. And then here for Weyl semimetals, I give you the corresponding expression in Fourier space. So if you have a nucleus that's localized in real space, so if an electron comes in with momentum K, it gets scattered off the nucleus, and then it goes out with a different momentum K plus Q. So Q, that's the momentum transfer of the electrons due to scattering of the nucleus. So this is Q here. So here the first term is the orbital term. So apparently here the physical spin of the electron appears here. So this is not the orbital angular momentum, but something else. So if you do the pair substitution, this is the expression what you end up with. So even though this looks like the orbital term from the derivation, it also contains the physical spin of the conduction electrons in Weyl semimetals, in sharp contrast to what happens in normal metals. And there is the second term, which is the Fourier transform of the spin dipole interaction, which also contains the Fermi contact interaction. And so one thing to be noted here is that Q, that's the momentum transfer. So what happens if Q goes to 0? So if Q goes to 0, this term, the spin dipole term, scales as q square. There is a q square term downstairs. So altogether, these two guys cancel each other. So the spin dipole term looks rather harmless in the q to 0 limit. However, if we consider the orbital term, then there is only a single q upstairs, and there is a q square term downstairs. So altogether, this orbital term will diverge as 1 over q in the small q limit. And I will argue that this divergence will have some serious consequences for the spin relaxation time of well fermions. Now, this is the physical form of this is the Fourier transform of the hyperfine interaction. And so if we want to determine 1 over T1T, we can just use Fermi's golden rule. So this is a lengthy but rather straightforward calculation. So we end up with an effective one-dimensional integral for the spin lattice relaxation time, what I'm not going to show you. I'm just showing you the limiting cases. So here, this is 1 over T1T in dimensionless units. And here there are some prefactors. But then the interesting finding is that 1 over T1T scales only as T square in the high temperature limit, as opposed to the naive expectation, which was T to the 4. While if we go to the small temperature limit, it only scales with mu square, as opposed to mu to the power of 4, which came out from textbook considerations. So apparently there is a different scaling compared to what you expect from textbook expressions. In addition to that, there is also a logarithmic correction which contains the nuclear Larmor frequency. So this is the magnetic field here. So at large temperatures, there is a T over magnetic field. And then at large chemical potential, there is a mu over a magnetic field term here. But it turns out that this logarithmic type of divergence, so you can imagine that as you lower the magnetic field, it will blow up logarithmically with the magnetic field. This is not really important because this is only there for pristine, very clean well semimetals. However, if you put in some impurities, disorder, electron-electron interaction, so you name it, whatever gives you a finite lifetime, this Larmor frequency will get replaced by that energy scale. And then this divergence with the lowering of the magnetic field will disappear immediately. And also this logarithmic dependence is not so important. What is important here is that the power of T and the power of mu changes from 4 to 2. So if we want to put this into perspective or analyze this using this expression, so there are two options. So one option is that the density of states in well semimetals is linear in energy, and then that would explain these findings. But this is not the case. We well know that if you have a very clean well semimetal, the density of states behaves as the square of the energy. So the other option is that this hyperfine coupling is not constant, which is a usual assumption in various textbooks, but it has some peculiar energy dependence. As a result of that, we can cancel one of the exponents, one of the powers for well semimetals. And so our argument is that due to the fact that this first term diverges as 1 over q in the small q limit, this can be interpreted as having an energy-dependent hyperfine coupling for this orbital hyperfine interaction, which diverges as you approach the well point. So if we assume that we have a hyperfine coupling which diverges as 1 over the typical energy scale, so either the chemical potential or the temperature, then if we combine that with that expression, with the density of states of well semimetals of this form, then this formula makes perfect sense. But still, this is surprising to have a hyperfine coupling, what you can tune by the temperature or by the chemical potential of your system. Let me also mention that if you consider the spin dipole part of the interaction, it gives the expected contribution, namely that it scales with the maximum of mu to the 4th or T to the 4. So this is how far we got with the theory. And so this part, these results sounded kind of suspicious to us. So we thought that at small temperatures or for small chemical potential, this term should be dominant over that. But maybe it can happen that the prefactor is really tiny. So even though in terms of temperatures, in terms of exponents, this orbital hyperfine coupling should give us the dominant term. But if it has a tiny prefactor, then the conventional expression survives. And so nothing peculiar happens here in Weil semimetals. But at this point, so this was kind of unusual, because usually what happens is when you do a theory, in many cases you try to explain an experiment. But here this was the other way around, because when we posted our paper on the archive, we got contacted by Hiroshi Yasuoka and Michael Benitz saying that they measured the relaxation time in Weil semimetals in tantalum phosphorus, and then they found the exact same behavior but we predicted by our simple-minded theory. So this is just a one-slide summary of the experiment. So this is tantalum phosphorus, and then to be more precise, they did not really perform an NMR, but they performed an NQR experiment. So this is nuclear quadruple resonance on tantalum. So I was told that I should not worry about the fact that this is not NMR but NQR, because it measures the very same 1/T1. So then I stopped worrying and then started to analyze that data. But before telling you the details here, let me just present the band structure calculations based on DFT for this tantalum phosphorus. So there are many bands, but here this is just a highlight of two bands. So at 0 temperature, this is the Fermi energy. And there are two Weil points at the close vicinity of the Fermi energy. There is one upstairs, roughly at 13 millieV. And then there is another Weil point downstairs, down by like 41 millieV. So probably this Weil point is closer. So this is kind of more important in terms of the low energy dynamics, because even if you go up to room temperatures, there is no chance that you can probe this Weil point, which is like 400 Kelvin away from the Fermi energy. And so this is the density of states. This is the Fermi energy. And this is where typically the Weil point above the Fermi energy is located. And so they took this material, tantalum phosphorus, and then they do an NQR experiment on tantalum because it has a quadruple moment, because this is not spin 1/2, but if I recall, this is spin 7/2. So in principle, it can have a quadruple moment. So if you just look at a closer look at that, these red squares, these are the experimental data. Grosso modo, it reproduces the theoretical expectations, namely that at low temperatures, this is roughly constant. So this is what is expected on general ground. While if you go to high temperatures, much higher than the chemical potential, then 1/T1T should increase with the temperature. However, the exponent, what they find here is not 4, so not in accord with simple textbook considerations, but the exponent, what they find here is 2. So the exact same exponent, what we predicted by our simple-minded theory. So apparently this could be kind of the first experimental observation of this anomalous nuclear spin relaxation rate in Weil semimetals, namely that 1/T1T grows not as T to the 4th, but as T squared. But there is an additional interesting observation here, and this is that for small temperatures, 1/T1T is not completely flat, but there is also a bending down here. So initially we thought that this could be due to the temperature dependence of the chemical potential. However, if you recall your solid state classes, then what you learn here that even in a normal metal, the chemical potential can have some temperature dependence. So at 0 temperature, the chemical potential is equal to the Fermi energy. However, if you go to finite temperatures and then you want to preserve the total number of particles, you can only do that at the expense of introducing a chemical potential, temperature-dependent chemical potential in a ground canonical ensemble. However, as you increase the temperature, the deviations will be of order T squared over the Fermi energy squared. So in a normal Fermi gas, the Fermi energy is of the order of 1 electron volt, typically, so 10 to the 4th Kelvin. So there is no chance to observe that in a real experiment. So the deviations between the chemical potentials and the Fermi energy, these are just tiny. But if you repeat the very same calculation in a Weil semimetal, so you want to get the temperature dependence of the chemical potential by imposing the constraint that you want to preserve the total number of particles, this is the implicit equation what you get. So if you solve that, you find that the Fermi energy gets replaced by the zero temperature Fermi energy measured from the Weil point. So in this case, this is just this tiny chemical potential, which is of the order of 13 millieV or 100 Kelvin or something of the order of that. Meaning that as you increase the temperature, the difference between the zero temperature chemical potential and the Fermi energy and the finite temperature chemical potential will grow significantly with increasing temperature, because the corrections are of the order of T square over mu square, while here mu, so the typical Fermi energy or zero temperature chemical potential, is of the order of 10 or 100 K, or something of the order of 10 millielectron volt. And so if you solve this equation, this is this green curve, what you get for the ideal temperature dependence of the chemical potential in a clean Weil semimetal. So this is definitely not a clean semimetal. So we put all of our ignorance about the band structure into an approximate formula. This is this blue curve here. This is just a Lorentzian. So it goes down in a T squared manner, and then it vanishes at large temperatures in a 1 over T squared manner. So this is just a very simple approximate formula, what we use for the temperature dependence of the chemical potential. But if we use that, then we can just describe perfectly within error bars the experimental data, including this nice downturn of the 1 over T1T, which is, as we argue, due to the temperature dependence of the chemical potential. So if I want to summarize this part, there are two kind of interesting characteristics of the nuclear spin relaxation rate in Weil semimetals. One is that if you go to very high temperatures, 1 over T1T scales at T squared. And the other observation is that in many cases, you expect a downturn at first as you start increasing the temperature from zero temperature due to the temperature dependence of the chemical potentials. So this is a second interesting effect, what you can easily observe in Weil semimetals. So this was just one sort of Weil semimetal tantalum phosphorus, but there was another experimental group. This was led by Guosing Zhang. So they are working both in Beijing and somewhere in Japan. And they took another compound of this family, tantalum arsenide. So this is again an archetypical Weil semimetal. So they did an NMR experiment at zero temperature. So this is considered to be an NQR experiment, but they also considered another experiment at a rather large magnetic field, almost at 13 Tesla. And they found very similar features, namely that as they crank up the temperature from zero temperature, there is a kind of downturn in 1 over T1T, while as you crank up the temperature, there is this characteristic T square type of temperature dependence as you crank up the temperature. So this is fully in accord with our theory. And so in the meantime, there is also a third compound, which is thought to be a Weil semimetal. And so in the high temperature regime, experimentally, this T square type of growth of 1 over T1T was also identified in those materials. So this is roughly it, what I wanted to tell you. I planned for a 30-minute talk, and I guess I'm just within time. So let me give you my final summary. So there are some interesting observations for the NMR relaxation rate in Weil semimetals, namely that the orbital part of the hyperfine interaction is dominant over the spin dipole part, while for normal metals, the spin dipole part is dominant, and then more prominently, the Fermi contact interaction. So we can account for the temperature dependence of the experimental data by introducing an energy-dependent hyperfine coupling. And also the experimental data reveals the interesting temperature dependence of the chemical potential here, which is rather difficult to observe for normal metals due to the very large Fermi energy. So this is roughly, this is what I wanted to tell you today. So with that, I thank you for your attention.
Thank you, Balázs, for the nice talk. I think I think we are quite a few participants. So I think if you have any questions, then please put them in writing. And so we have 10 more minutes for questions, actually, so quite a lot. So please, anyone, if you have questions, then please do write them now. So there we have a question. Oscar writes, thanks, Balázs, for the nice talk. I'd like to make a question. The NMR technique could have corrections from surface effects. And could it be used to analyze surface effects instead?
Probably not. Probably not, because if you do an NMR, what matters is practically the volume, so the number of nuclear spins, right? So you always observe surface effects, but they scale with the area of the surface. But there is also another bulk contribution which scales with the bulk, so with the nuclear spins in the bulk. So the volume, so the surface to volume ratio is like A over V, and this is practically negligible in the thermodynamical limit if you have a really large bulk sample. So in principle, there is also a tiny contribution in the NMR signal, but there is no way that you can reveal that in your experimental data, I guess. So it should be there, but with the present techniques, when I talked to the experimental colleagues, I was told that this is just impossible to measure that. Also, this is also part of the problem why the NMR signal of graphene cannot really be measured, because in graphene, the bulk is the surface. But even if you take a typical graphene sample, the number of nuclear spins, assuming that all carbon atoms have a nuclear spin, is just not enough to make the signal observable.
Okay, thank you. If there are other questions, if there are no questions in writing yet, I have my question as well.
Laszlo, sorry,
yeah?
I do have a question. I was trying to write in the chat. So, okay, there is a question by Henning.
What is the role of other relaxation mechanisms?
This I don't know, right? So that's a good question. So nuclear spins can interact with other nuclear spins. Yeah, they can interact with valence electrons and whatnot. So we did not really analyze that. We just focused on this particular contribution, and then it described the experimental data. But it is not really obvious why and whether the other contributions should give this T-square type of behavior. So we don't know that. But these are the typical contributions that if the nuclear spins are close to each other, they can interact with each other, so that can be a significant contribution. Plus, you can have interaction with the bulk electrons, so not with the conduction electrons, but the valence electrons. So that can also give some probably constant 1 over T1T, assuming that the density of states is constant. But we did not really analyze that. And also, this is a low energy effective theory, so we don't have access to those guys. So if you want to analyze those contributions, that you need to use a DFT or kind of more ab initio type of approach when you take other bands away from the Fermi surface account.
Thanks, Bella. I have perhaps I'm going to try to make a short question. So in thallium phosphide, you show that there are bile points close to the Fermi level.
Yeah.
But also there are other bands or bile points, but well above the Fermi level. So we can consider those bands as a more conventional band, right?
Right.
That will give you, as you show at the beginning, that they should contribute as T to the fourth, right?
Well, not really, because what NMR does is that it probes the close vicinity of the Fermi energy within a window set by the temperature itself, right? So even if you are at room temperatures, so you are like 300 Kelvin away from the Fermi energy, there is no chance that you can probe electrons, say, at 500 Kelvin, simply because the temperature window is not enough. So, I mean, that's the main merit of doing NMR, that it probes only the close vicinity of the Fermi surface, probably.
Yeah, but
So
for the other pocket, there are more conventional. So
you mean down here? Yeah, okay. So yeah, you mean that this is like a more conventional contribution, so this should give us so this is probably just a constant contribution. So instead of doing this fit, what we could have done is to like assume that there is a constant contribution coming from this like normal metallic band, plus this other contribution coming from very semi-metals. But you know, that would make the fit probably less convincing, because if by neglecting this contribution, we can make such a nice fit. We can just assume that this guy gives us very tiny contribution, a very tiny constant 1/T1T, which is probably down here. So at the expense of varying these parameters a little bit, we can get a similar quality fit. So that would just increase the difficulty of the fit, or it would make it kind of less believable, because it would introduce some other fitting parameter, because here we just don't know the hyperfine coupling and the density of states. I mean, even the density of states that can be extracted from the DFT, but we don't really know the value of the hyperfine coupling here. So that would be another fitting parameter. But in principle, you are right. So if you want to analyze this rigorously, you need to add these two contributions together. So one from this whale-like band, and another from this other band, which is just normal metallic.
Okay, thank you, Balázs.
Thanks for the question.
Still have 4 more minutes, and I also have a question.
Okay.
So am I correct in assuming that when you had the Hamiltonian for the Weissami metal, you assumed that sigmas were just proper spins?
It does not really matter for that. So it matters for the night shift, but for this, it does not really matter, simply because if you do the pair substitution, you just shift P, so this sigma, whatever it is, it remains. But when you introduce the Zeeman term, then there is the B dot sigma, so that's the physical spin. But it turns out that these two guys do not interfere with each other. So the orbital term gives a contribution by itself, and then the spin term gives a contribution by itself. But there is no cross term, which is like half of it coming from the orbital, half of it coming from the spin. That vanishes. So if that term would not vanish, then that would be interesting, because then it would make sense to consider other situations when this sigma here is not the physical spin, but just a pseudo spin, because then we could have some interference between the pseudo spin part of the Weyl dispersion and then the physical spin part coming from the Zeeman term.
Okay, so even usually these sigmas are somehow a mixture of the real spin and the orbital spin.
Right, right. But it does not really matter for that. So we also try to analyze the night shift. So the position of the resonance for the night shift, it really matters whether this is the physical spin or just a pseudo spin or just a mixture of those. So you can get different results depending on what that sigma is, but not for 1/T1T.
Okay, thank you. Are there any more questions? So we still have 2 more minutes. I think if there are no other questions, Alberto, what is the procedure? Do we wait for questions for 2 minutes, or do we go on with the next talker?
So I think we can go to the next talker, because we are on time, right?
Yes, we are on time. So it's 10:10 actually. So I think we can move to the next talker, and the next talker is Zoltán Tajkov from the Eötvös University, and he's going to talk about competition of trivial and topological fields in graphene-based hybrid systems.
Okay, good morning, everybody. First question, can you hear me?
Yes.
Properly, can you see me?
Yes.
Okay, and can you see the share screen?
Yes.
Okay, so everything is perfect, I can continue.
And your clock is starting now.
Okay, so first of all, I would like to thank the organizers for having me. I am Zoltán Tajkov from Budapest, from the Eötvös University. And today I want to talk to you about how can we make graphene a topological insulator. So probably I do not have, sorry, can you see the cursor as well? Because I'm going to use it.
Yes.
Okay, thank you. So probably I do not have to introduce you graphene. You all familiar with its peculiar mechanical and electronical properties. And what really makes graphene interesting for us is that it makes a really good template for devices, heterostructure van der Waals devices. The problem with graphene from a semiconductor industrial point of view is that it's more like metallic than an insulator. So I address a question that how can we make graphene a topological insulator is there any way that we can do about it? This question is answered since 2005, since Keane and Mela wrote this paper about the quantum spin Hall effect in graphene, and they showed that actually graphene is a topological insulator due to the spin-orbit interactions in graphene. The only problem is that this spin-orbit coupling in graphene, due to the small weight of the carbon atoms, is actually really weak, so we cannot really exploit this effect in practice. So my question is, how can we somehow induce the spin-orbit coupling in graphene to make it much more stronger, so we can use this material more efficiently? And because we have a really good way to build heterostructure devices, van der Waals heterostructure devices, is there any material that we can use to build a device based on graphene that we can use? That's going to be the question. And let me introduce you the bismuth tellurides. Probably you are not that familiar with this material family. So this is basically, as you can see in the top left corner, it consists 3 layers of bismuth in the middle, 1 layer of telluride, and from the top it can be iodine, bromide, or chloride as well. So it's actually 3 different material. What is common between them is that the bond between the layers in this structure is ionic, so it's a covalent bond. But between the units, the interaction is van der Waals type. So it makes Hello?
Hello? Ah, you're back.
That's great. So let me share my screen again. Does anything working at all?
Please, yes, go ahead. Yeah.
Okay, sorry about that. I hope it's never going to happen again. So I don't know where I was. So here you can see the bismuth telluride. What is really important about this material is that it's a van der Waals material, so it's a good candidate. And the spin-orbit coupling in these BTEX materials is really big. So probably it can help us to induce the spin-orbit coupling in graphene. That's going to be my approach. The first question that we have to answer is that can we exfoliate this material to have just 1 unit of the 3 layers to put it onto graphene? The answer is yes. In 2018, it had been reported that on gold surface, the experimental physicist could exfoliate it was actually the beta, which means that iodine was in the on the bottom layer. So it can be done. From now on, let's switch back to the theory and put this material on graphene in a computer, and let's see what happens. This is our geometry, and there is no any over-exaggeration in the picture. The graphene and the BTEX really can fit together this well, as you can see here. The misfit between the unit cell vector of graphene and the BTEX is around 1%. So this is going to be our configuration, and let's see what the DFT says. This is the band structure of around the Fermi energy of the whole system, and as you can, maybe you can recognize the direct cones of the graphene here. It's really altered due to the presence of the BTEX, and it seems like it's metallic, but if you look closer, there is a tiny gap, less than 1 milli-electron volt, and that gap in a topological sense is trivial. So right now it seems that this configuration does not really help us. Maybe there is something that we can do about it. Maybe you are familiar with the fact that if we apply mechanical distortion to anything, not just graphene, but to graphene specifically, then we can have a really big zoo of different electronical property. So my approach was that let's see what happens if you apply some mechanical distortion to the whole system. What mechanical distortion am I talking about? For example, pressure, it's really easy to do in DFT. Pressure means for us now that we are just reducing the distance between the two layers. And in the meantime, as we are applying pressure, we can apply uniaxial strain to the whole system as well. So this is going to give us a phase map where every point is some pressure and some uniaxial strain value. And at every point, I'm going to calculate with DFT the band structure. I'm going to look at whether is there any kind of gap. And if there's a gap, I'm going to calculate if it's trivial or topological. So here are the phase map from DFT. As I said before, we have 3 different materials in the BTEX family. I'm just going to explain one phase map here, and then you can see what's the difference and the similarities between the materials. So let's look at the B-type bromide, for example. And in the horizontal X, you can see the pressure, which the pressure right now means that we are just reducing the distance between the layers. That's pressure. And on the vertical X, you can see the uniaxial strain that I applied as well to the system. The origin here in the right bottom corner is the equilibrium point where there is no any kind of pressure or strain on the system. And the color coding of the map is that the gray area, or it should be a line, but the gray color means that the gap is small, let's say, around 0. The red color means that it's trivial, the gap, and the blue means that it's topological. So let's start from the beginning in the origin. This is the equilibrium, and we apply pressure to the system. That means that we reduce the distance between the layers, and as we go in this axis without any strain, eventually the originally really tiny trivial gap going to be larger and larger, but it's going to remain trivial. If we go back to the beginning and then apply strain without any pressure, you can see that the gap is going to be wider again, and in this case it's going to be topological. And at any point, for example here in the strain, we apply pressure to the system, then it's going to be smaller, the gap is going to be smaller and smaller, eventually it's going to be closed and then open again, but it's going to be trivial. So it seems like that if we apply pressure to the system, it promotes the trivial gap, and if you apply strain to the system, it promotes the topological gap. Can we understand why? That's going to be the question. We learned 2 things from the DFT that you have to believe in, because I do not have to prove it to you. But the one is that we have 2 important parameters from that act on the graphene. One is that
You are back.
it's getting annoying. Sorry about that. Are we back?
Yes, you are back.
Okay, sorry. So we have 2 important parameters that act on graphene. The one is the so-called Kekulé pattern. That means that the carbon-carbon bonds altered like a benzene ring that you can see here. So the red and the black bonds are different in strengths. That's the Kekulé pattern. And the other is that I mentioned before, the second nearest neighbor kinemaila type spin orbit coupling in graphene, which has the same alternation as the Kekulé. These are the 2 most important parameters that acts on the graphene. And it seems that strain, for some reason, promotes the spin orbit coupling, which means that, I don't know why, at this point we don't know why, but it seems that if we apply strain to the system, then the spin orbit coupling is getting stronger and stronger, and that's why it became a topological insulator. But why? That's the question. And we built a tie binding model that consisted the strain, the uniaxial strain, the kinemaila type spin orbit coupling, and the Kekulé. And instead of explaining to you these really nice equations, I brought you some simulations that I want to show you I don't know whether you can see it or not. I hope you can see. This is the dispersion relation of the graphene without any distortion. So this is the basic tie-binding graphene that you can see. What happens if we apply strain to the system? Then the originally Dirac cones are going to split, and then as we apply more and more strain, they are going to just shift away from each other. Okay, that's the effect of strain on the graphene. If we apply the Kekulé type of distortion, as I showed you before, this is going to open a gap which is going to be trivial. Okay, and if I apply the spin orbit coupling, it also opens a gap, but it's going to be topological. Now let's see what's the effect of strain to these two. If I open a gap with the Kekulé, then the strain, if I apply strain now, is going to try to close the gap. Eventually it succeeds, and then if I apply more and more strain, then no more gap will open, and it's going to be metallic. Now let's see what happens if I open a topological gap with the spin orbit coupling, and now I apply strain to the system. From the perspective of the gap, we can say that nothing actually happens. The gap is going to be the same. I have a I summarized these findings in the next slide. Here you can see the gap, the value of the gap versus the strain. So first, we do not have any Kekulé, but only the spin orbit coupling is turned on. And if we apply strain to the system, as I showed you before, the gap is going to be the same constantly. Next, if we switch and turn off the spin orbit coupling and just turn on the Kindle type distortion, and we apply strain to the system, as I showed you before, the strain is going to try to close the gap. Eventually it succeeds, and then it's going to be closed. If we have a Kekulé type distortion, which is stronger than the originally spin orbit coupling, then we are going to have a gap which is trivial. And then as we apply strain, it's going to close the trivial gap, and then the topological gap opens. But if we have both, but the spin orbit coupling is stronger than the Kindle type distortion, then we have originally a gap which is topological. And when we apply strain, the topological gap remains, but it's going to be stronger and stronger. So what actually happens in this case is not that this strain somehow make the topology, the spin orbit coupling stronger. What actually happens that we had two effects that had a competition in the graphene: the Kekulé type distortion and the Kindle type spin orbit coupling, and they were balanced in the beginning. But then as we apply strain, it's not happened that the spin orbit coupling getting stronger, but the Kekulé type distortion became weaker and weaker. And that's why we saw that the topological gap opened in the graphene. I don't know how much time I have left, but I think I'm close to the end. So I'm going to thank you for your attention, and that's all. Thank you.
Okay, thank you, Zoltán, for the talk. So there were two questions in the audience so far. I mean, also everyone else, feel free to write more questions if you like. So first question came from Alberto. Applying pressure does the same effect in beta and in graphene, or some misalignment should appear?
So what happens if we have beta and can you repeat the question, sorry?
So if you apply pressure to, does the same effect happen in the bismuth telluride, or sorry, you are again kicked out. Yeah, you are back.
Okay, so I think I heard the question. So what happens if, so is there any difference between the beta and the beta brom, for example?
No. So do you have to do, can pressure do the same different things with graphene and bismuth telluride? At least, I mean, Alberto, clarify me because it was your question. So
Okay, so the question is when you apply pressure, you
Yes.
said at the beginning that the lattice, the lattice of graphene and these BT systems are pretty much the same. So they are commensurate somehow. So when you apply pressure,
Okay.
do you expect this commensurability to be maintained? Or do you expect some inhomogeneities, for instance, in graphene to appear?
Okay, okay. That's a great question. On the scale that we were inspecting, nothing actually happened to the. So in the DFT, we let the system to relax due to the pressure. So we did, for example, if you have when we had pressure, we reduced the distance between the layers, but we let the whole system to relax in the atomic level, but we didn't let the layers to move apart. And on this scale that we were inspecting the system, no any inhomogeneities happened. But probably if you pressurize more and more and more, then I can imagine that something like this happen. I don't know whether I answered your question.
Okay, thanks.
Okay, thank you.
And there was one more question from Balázs Dora. Can you also twist your layers as in twisted bilayer graphene? Do you expect new features?
Okay. We haven't checked what happens when you twist the system. Well, probably it depends on the twist angle. So if you twist it enough, like 30 degrees or something, then nothing actually happens, I think. But probably if you find some incommensurate structure, then I can imagine that the whole effect is not going to be the same, because it is really coded in the structure of the distortion and in the symmetries of the distortion. So if you break the symmetries of the distortions, whether it's Kekulé type or Kekulé, then probably the effect is not going to be the same. Probably, for example, to apply uniaxial strain to the system is not going to be too easy to handle. Am I kicked out again, or no? No, I'm here. Okay.
Okay.
Okay, thanks.
Okay. So
Thank you.
New question from Henning. Is strain still giving you a pseudo-vector potential, or the effects are more complicated in these systems?
You mean the okay? So pseudo-magnetic vector potential. I think that's the question, because yes, we have pseudo-vector potential, but probably it depends on the strength of the strain as well. So in our case, the strength of the uniaxial strain was really small. So I think it's, I don't know if I'm sharing my screen or not, but in our case, the strongest value of the biggest value of the stream was around 1%.
Thank you for the answer. Henning?
I don't know whether I answered the question.
Okay. Okay, so now the next speaker is apparently not around. So I think we are forced to make just in the same fashion as it's common in the March meeting. We are going to go for a short break of 20 minutes. And we are going to get back to the talks at 10:50. So far, I think we can just use this time to chat. I don't know, Alberto, we can open the mics, maybe?
We can what, sorry?
We can open the microphones. Maybe we can also allow for a bit more discussions regarding the first two talks.
Yes, let me see how to do that. I think the participants can now switch on their phones now, I guess.
Yeah.
So all of them are muted now, but if there is anyone who wants to make a question, till 10,
I think Balázs still had another question in the chat about the twisting. Did you actually address this?
We missed, yeah.
Okay. So I think I can actually, I can partially answer that question as well, because we did some calculations regarding that. So the problem with the twisting, of course, is that, so if you go from the point of view of tight binding and the DFT calculations, you quickly go to pretty large systems. But sort of our feeling in these systems is that the induced spin orbit coupling is quite decent, pretty large, and there might be some other effects which compete with it, but it is much more robust compared to these other effects, just for example, as we have seen in this strain. But we have not done any conclusive proper calculations yet. So the strength of the induced spin orbit coupling could depend on the twist angle, and thus, but it seems that the induced spin orbit coupling almost always promotes the topological a topological insulator, and it is not something like a Rashba coupling which would kill it. So it's an interesting question, and we certainly have done some foyers in that respect, but we don't have any conclusive results yet.
But do you see any flat bands or like what is seen in twisted bilayer? Or
no. So the thing is that in these systems you have graphene with just a proper Dirac cone, and these bismuth halides have a relatively large gap.
Okay. Mm-hmm.
So you don't really expect the flat bands to be present, but you expect the Dirac cone to undergo some sort of minor perturbation, which could maybe lead to an opening of a gap or something like that. Mm-hmm. But you don't have this. I mean, you certainly don't have these two Dirac cones strongly messing each other up, as in bilayer graphene.
I see.
Okay. Yeah. So I don't know if there are other questions regarding. Actually, I wanted to ask you, Balázs, what do you think if you would go to nodal semimetals from base semimetals in your case?
This is a good question. I don't really know. So I guess the calculation what one needs to do is pretty clear. So you just need to repeat the very same thing. So I can foresee some anisotropy, right? Because if you have this nodal loop, then the direction matters, but somehow 1/T1, the average is over that. So I don't know, maybe it also depends on the direction of the magnetic field. I don't know.
Okay. Yeah. So yeah, it's a pity that the talker is not here because there are so many people around. Yeah.
Can you ring him or like send him?
He didn't even came to the last week's
okay.
thing, so we don't even have any handle on him to see. But there is also the okay. Okay, so I think yes, we can go back to the.
Well, if you look at the abstract, the research of the speaker has been published, so we can all read the paper when we want.
That's actually a good point. So it is published in Physical Review Research, and it should be interesting. Yeah, it can happen that he's still asleep because he should be in the US. At least his affiliation is in the US. This is one of the problematics with the online conferences, that you have to get people to the webcam in weird times. So it's okay. So I think we can restart the session. And thank you everyone for staying and not leaving. And it is really great that you are again coming back, even. So next speaker is Bailun Wu. And sorry, I need to get the titles of the talks.
Okay.
Is going to talk about angular-dependent magnetoresistance in topological semimetals, platinum, bismuth, and ruthenium. Okay, please, Bailun, start your talk.
Okay, thank you, Chairman. So can you see the slide?
Yes, and do you want to use your mouse?
Yes.
Yes, we can.
So, okay. So I'm going to talk about a bit of experiment, and I'm going to discuss about some transport studies that we have made in a few topological semimetals that we have measured. So recently there has been a lot of focus on the magnetotransport properties in some semimetallic systems, including some wire semimetals and Dirac semimetals, as has been mentioned in the previous talks. And also they include some other systems, many other systems that even have non-trivial, even have trivial band structures. So what is common in all these systems is that the magnetoresistance can go to a strikingly high level. As you can see here, that this corresponds to a thousands of even tens of thousands of increase of the resistance on the field. And they don't show a saturation at high field, and all these are very unusual in terms of classical understanding of magnetotransporting metals. And also some of these systems show a very unusual linear behavior. And the linear magnetoresistance is has been observed in a couple of systems, and generally there's no good understanding of theoretical from a theoretical point of view. And there are a few proposals. The first thing is to mention is a theory proposed by Abrikosov, which states that a linear dispersion in the band structure will lead to a linear magnetoresistance. And this, of course, is very exciting because it associates a transport property to non-trivial property in the band structure, and it is something that has been discussed a lot. For example, in the surface transport in topological insulators. But if you look at the semimetals, if we look at the transport in their bulk state, the situation is much more complicated. First of all, we have in a semimetal, usually we have many bands that cross the Fermi energy. And so although some parts of the band structure is topologically non-trivial, at the end of the day, you need to average over the whole Fermi surface to account for the transport properties. So to apply Abrikosov's theory, which is basically a single band theory, it is not a easy issue. And secondly, for experimentalists, the magnetotransport properties can change from one sample to another because it is strongly influenced by the sample quality. And associated to this, there's an alternative proposal which states that in a highly disordered system, a linear magnetic resistance might come from a complex current distribution. And also in some cases, strong electron correlations can also come along. And for example, it is used to explain the linear magnetic resistance in some charge density wave systems. And to discuss about magnetic transport in semi-metals, there is one factor that often plays a dominant role, and it is a ubiquitously present factor. It comes from the compensation of electrons and holes. So actually, this is something very classical, and it has been known since a long time that nothing but having equal number of electrons and holes in the system will lead to a B² increase of the magnetic resistance, and there will be never a saturation. So this simply comes from the fact that one needs to add the contribution from both electron and holes in the conductivity tensor. And when you have a perfect compensation between the two types of carriers, the off-diagonal terms will be zero, and this leads to a B² behavior in the resistance. And this is, for example, what is observed in the famous vial semi-metal tungsten ditellurium. And in some other system, the compensation is not so perfect. So, but the magnetic resistance will be slightly lower. It will not follow a B² behavior, but something similar. And a saturation may eventually come, depending on how good the compensation is. And there's another effect that might strongly influence on the magnetic resistance is the topology of the Fermi surface. So as you can see here, the Fermi surface of copper compared to sodium is fundamentally different because it touches itself on the edge of Brillouin zone. So in such case, on the magnetic field, the electron orbits can extend itself, can pass through these bridges and extend itself into neighboring cells, forming complicated shape like that. And in some circumstances, the electron orbits can extend infinitely and globally following a straight line. So these are the open orbits, and the influence of these open orbits on the magnetic resistance has been extensively studied. For example, in copper, that they have found that we have a small magnetic resistance at the majority part of the angle, and at the very angles where these open orbits appear, the magnetic resistance is strongly enhanced in form of peaks. So it's within this context that we are going to talk about. The first system that we have measured is platinum bismuth 2. And this is one of the semi-metals that shows the strongest magnetic resistance discovered so far. And the gamma phase of this compound has a hexagonal layered structure. And if you look at the band structure calculation shown here, there are many bands that cross the Fermi energy, leading to up to 6 Fermi surface pockets. And one of them, the gamma band, is formed with these sphere-like bubbles interconnected with each other through these necks. So we do have a situation that the Fermi surface is open in at least one of the band. It's not always the case in semi-metals because usually the Fermi surface are small, but it's the case here. So we took one single crystal and measured the angular dependence of the magnetic resistance in this system up to 20 Tesla. So we use a homemade mechanical rotator to change the field angle, and we keep the magnetic field in the plane perpendicular to the current. So it's only transverse magnetic resistance that has been plotted here. So as you can see, when we rotate the field away from the C-axis to perpendicular to the C-axis, there is a steady increase of the magnetic resistance. And at the same time, we see it's very nice change of the curvature from a downward saturating-like behavior to a non-saturating quadratic-like behavior. And we can fit the part of the curves of above 5 Tesla with an empirical power law, and the exponent alpha just increase steadily with the angle. So at one particular angle in the middle, at this 8.3 degree, we show that there's a very nice linear magnetic resistance that we have followed up to 22 Tesla. And this is something that we want to discuss. But before doing that, I just mention briefly that there's a small, if maybe you can see well on barely on the curves, there's a very small but well discernible oscillation signal. So this comes from we can extract the background, and it's a nice oscillating pattern. And this comes from the quantization of the electrons into the Landau tubes. And then the Fourier transform, in the Fourier transform, we can resolve many peaks, and they correspond to different maximum or minimums of the cross sections of different bands. So we can follow this as a function of the angle, and this tells about the geometry of the Fermi surfaces of this system. And our measurements compare well to previous quantum oscillation data and the band structure calculation. And what is important here is, I'm sorry, as we can follow the field slowly with our superconducting magnets up to 22 Tesla, we resolve much better the high frequency orbits. And now let's come back to the magnetic resistance in this compound. So we want to understand what we have measured. And the first thing to keep in mind is, of course, the semi-metallic nature of this system. So we have both electron and hole carriers present at the Fermi energy. And we don't have an exact compensation, but a close one. As this can be seen in the Hall effect measurements, because the Hall coefficient does not increase linearly with the field. So this is the first thing to take into account. And the second thing to mention is this open Fermi surface of the gamma band. So if you look at it closely, it actually consisted of, like, the 3 bubbles here are slightly higher than the 3 others in the center. So actually what is formed is something like a undulated honeycomb lattice, like in the plane perpendicular to the c-axis. And if we look at what happens on the magnetic field, we see that when we tilt the field slightly away from c-axis, for example, in the first plane perpendicular to the field, the electron orbits will go through the necks on the right side of this Brillouin zone, but not on the left side. And this will naturally lead to formation of open orbits. So we do have a situation that the open orbits come along, and so needs to be taken into account when talking about the magnetic resistance. So what we do is establish a simple model. So there are 6 bands in the system, but to minimize the number of free parameters and to simplify our life, we just suppose that there's no anisotropy of different bands, and all the electrons and holes have the same mobility. So we come naturally into the classical two-band theory, and we have a parameter D defined here, which characterizes the level of electron hole compensation. And on top of the two-band model, we have to add a small contribution from the open orbits, as electrons on the open orbits basically follow a straight line, and it's not deviated from by magnetic field. So it basically it's a constant term that needs to be added here. So we can see that this simplified model, with a good choice of all 3 parameters, it can reproduce nicely the data that we have measured at all the angles. And in particular, the open orbit contribution comes into play in a small angular range close to 0 degree. So the nice point of this model is that it reproduces nicely the linear behavior that we observe in this particular angle. And if we don't take into account the open orbits, it's basically the classical two-band model based on electron hole compensation. And you can see that it never reproduces this linear behavior. And there is always a visible saturation behavior in the high field region. So we explain our data with this model, taking into account two classical effects. And something that has not been mentioned is that this model does not include any elements of non-trivial topology. And actually, there's something has been suggested that this compound in the electronic structure, there is a triply degenerate point. We do not include anything associated to that because it's far away from the triply degenerate point is far away from the Fermi energy itself. And it corresponds to a very small band of holes. So we think, at first thought, it's not going to influence strongly the transport property of the whole system. So with the time that I have left, I'd like to talk about the second system that we have measured. It's ruthenium-2 tin-3. It's a very old system and belongs to the class of not Watney chimney ladder compounds. So this system have a very interesting crystal structure. Like the tin atoms, they arrange themselves in the helix strings, and the ruthenium atoms, they are surrounded by 12 tin atoms in form of a cage. So so this system has been found like 40 years ago, and it's tetragonal in the room temperature, and when cools down, it undergoes a very graduate transition into a orthorhombic state. And at the same time, this corresponds to small change of position of the tin atoms, and at the same time, the unit cell is doubled in the transition. And in the temperature dependence of resistivity, we have a broad maximum corresponding to this transition, structural transition. So recently, this system has been proposed to be a new candidate for topological insulator because due to open orbits, in the low temperature orthorhombic phase, there's an inversion of two bands, and that opens a gap exactly in the same situation as in other topological insulators. But what is different? Oh, sorry, that'll be quick. So, but we have finite bands narrowly crossing the Fermi level. So it's the bulk state. Unfortunately, is a low carrier semi-metal. So there have been RPS measurements that observe an isotropic Fermi surface. So basically, we have measured the magnetic resistance. It shows a linear behavior that persists up to very high temperature. But the point to take here is that it's not, we are not dominated by surface transport. As you can see, in the angular dependence, it shows the orthorhombic symmetry pattern of the bulk state. So this is something associated with electron-electron correlation in this system due to the structural transition. So before finishing, I just mentioned quickly that we are setting up our STM measurements at high magnetic field and a low temperature, and there has been tremendous progress in the performance, and we plan to measure some nice unconventional superconductors in the future. And I'd like to thank the people that I work with in Autonomous University, and with this I leave you with a summary, and thank you for your attention.
Okay, thank you, Bailun, for the nice talk. So we have short time for a couple of questions. So first question is from Alberto. You focused on transverse MR. Do you have measurements of longitudinal one? Do you expect something interesting like linear magnetic resistance in the longitudinal magnetic resistance?
I'm sorry, do you a question about measurements of NMR? Oh,
so sorry,
I didn't get the.
You focused on the transverse
yes.
resistance. distance. Do you have measurements in the longitudinal one? Or do you have something interesting in longitudinal measurements?
No, we didn't do that. We chose to, yeah, actually you can see nice chiral anomaly in longitudinal, but it's something really hard to, like it's hard to tune. We have 1x rotation and it's hard to tune the field exactly in the same direction of the current. So we didn't choose to do that experiment.
I also have some, is it okay, Alberto? Do you accept the answer? I think, okay, he says, okay, thanks. I also have a single question regarding, you showed a slide about the oscillations.
Yes.
And you shown that you have made some analysis of the surface cross sections, but did you do also look for the phases of the oscillations? So could you look at the whether the very phase of the oscillations? Or
yeah, it's a very good question. Actually, we do that in one of the band, the smallest band, because basically in all the other bands we observe oscillation very far from the quantum limit. So it's you can do a linear fit to get a phase, but since you are too far away, it's not the exactitude is not really reliable. So we did it for the beta band, and it kind of supports the fact that in previous quantum oscillation data that they claim a non-trivial topology from the phase of quantum oscillation in the beta band associated to the triplet degenerate point. And but this is something really hard to do because we have frequencies just really close to the frequency, and you need to filter the signal very properly, and it's not easy. So we have hints on that, and we have tried, but it's not really robust analyze.
Mm-hmm. Thank you. I think we have to move on. Thanks again for your nice talk, and thank you for contributing. So next talker is Iñaki.
Okay. Yes.
And Iñaki is going to tell us about tunable and robust long-range coherent interactions between quantum emitters mediated by wave bond states. Please, Iñaki.
Okay, so I hope you can see my screen.
Can you go to full screen?
Yeah.
Okay. Can you wiggle your mouse? So.
Yeah, it's here, right?
Yes, we can see your mouse as well.
Okay. So thank you. Well, hello everybody. My name is Iñaki Garcia, and today I will discuss some line matter interaction phenomena that emerges in bi-like environments. So first of all, I want to acknowledge the people who I've been collaborating with to develop this project, Alejandro González Tudela and Jorge Bravo, and also the organizers for giving me the opportunity to present this work. Okay, so let me start with a brief introduction just to make sure that we are all in the same point. So in condensed matter physics, it was shown that low energy excitations of some three-dimensional crystals can be connected to massless solution of the Dirac equation. The dispersion relation of such periodic systems features the so-called Weyl nodes, which are points in a typical space where two linearly dispersed in band touch. Well, these environments actually call the attention of both the electronic and also the photonic communities. I'm focusing on the second one, since pioneer experiment in 2015, plenty of both experimental and theoretical studies has shown that these Weyl dispersions can actually be realized in a great variety of photonic platforms. However, line matter interactions therein remain largely unexplored, and this is precisely the problem that we have intention to tackle here. So to do that, we consider a prototypical scheme to study quantum optics phenomena, which is composed by a collection of emitters interacting with some kind of photonic environment, which is actually the most interesting part. So the idea is that to mimic such a Weyl system, we use a discrete lattice model, wherein localized bosonic modes interact among them through nearest neighbors couplings. particularly hopping patterns define two distinct sublattices, which translates into a two-bands dispersion relation with 4 different Weyl points. Okay, so even though the on-site energy of this bosonic modes can be taken to be the, or is taken to be the Weyl frequency, we can also add a position-dependent on-site energy offset, which allows us to move these Weyl points in reciprocal space. That's that, for instance, when m is equal to 2 in units of this hopping rate, we have that Weyl points with differential number merge, leading to a band opening, which is clearly observed when m is equal to 3. Okay, so recapitulating, we have our quantum emitters, modeled as two-level system and characterized by their detuning with respect to the Weyl frequency, the already explained photonic environment, and the interactions between the two previous components, which are assumed to be local and governed by this scalar parameter G. Okay, so we start investigating the case of a single emitter coupled to the bath, and in particular, we study the dynamics of the emitter excited state population, provided that the system is initially prepared with the emitter in its excited state and no photons within the bath. So perturbative treatments, as for instance Fermi-Golden rule, usually yield an exponential relaxation of the excited state population of the emitter with a rate that is proportional to the value of the bath density of states at the emitter frequency. So therefore, when the emitter's energy matches the Weyl frequency, this approximation predicts a non-decay dynamics. However, we wanted to gain a more general perspective of the problem, and that's why we resort to non-perturbative techniques, and in particular, the so-called resolvent operator method, which relies on the inversion of the propagator matrix element to obtain the excited state population of the emitter. Okay, so employing this non-perturbative approach, we compute the sub dynamics for the case when no energy offset is considered and the emitter is detuned towards the Weyl frequency. And as observed here, in contrast to the Markovian prediction, the excited state population of the emitter features an initial decay at short times, followed by a set of oscillations, after which it settles down to some constant value. Okay, so similar behavior is obtained when the on-site energy offset is different from 0. And while this type of incomplete decay can be actually interpreted as the signature of the emergence of what we call a photon-atom bound state. So I will go over it in a moment, but first let me just show you that by plotting the stationary state population of the emitter as a function of the on-site energy offset, we realize that the formation of such a photon-atom bound state is actually ubiquitous to the full range of m values, and namely when m is in between -2 and 2. This is when the Weyl points are still present in the path. The value of the stationary excited state population remains close to the one obtained for m equals 0. So henceforth, we restrict ourselves to this particular regime. Okay, so at this point, I think it's a good idea to say a few words about the photon-atom bound state, which were actually first introduced when studying the QED properties of an atom embedded in a photonic crystal featuring a complete photonic bandgap. So naturally, the radiation properties of an atom embedded in such a medium will be strongly modified, and in particular, they will lead to the formation of a hybrid light matter state in which the photons remain localized around the atom. So in the past few years, these bound states have received a lot of attention, and especially due to their potential to mediate long-range interactions between atoms. So the idea is that by embedding the emitters within a bandgap material, one can avoid the dissipative mechanisms that usually hinder the emergence of such long-range interactions. The price to pay is that standard bandgaps yields an exponential localization of the excitation around the emitter, and thus limiting the potential of the emergent bound state to mediate such long-range interactions. Well, this interaction range can be actually extended to display power law character by considering a photonic reservoir featuring a Dirac-like dispersion. But the problem then is minor perturbation of the system can lead to a band opening and thus destroy this long-range character of the interaction. So following this line of reasoning, biosystems stand as appropriate candidates to overcome all these limitations. Okay, so far we have focused on the dynamics of the emitter, spotting the emergence of this, let's call them bile photon atom bound state as the most interesting result. Next, we wonder how the considered excitation is localized around the emitter when such a bound state is formed. So note that the bound state wave function can be actually decomposed as the sum of an emitter-like component and a photonic component, which is characterized by these C sub R coefficients that can be actually computed through the time-independent Schrodinger equation. Okay, so here, for instance, I plot a three-dimensional distribution of the bound state profile when no energy offset is considered and where the color scale stands or indicates the magnitude of these C sub R coefficients. So in this case, we find that the bound state photonic component localized around the quantum emitter, mostly in an isotropic fashion. But to fully characterize the real space distribution of the bound state, we also study its long-range character along some specific direction. By doing so, we observe that the bile bound state photonic component features an inverse square power law confinement. Okay, so even though these power law confinements have already been reported in Dirac-like reservoirs, biosystems offers a unique advantage, and is the possibility to modify the dispersion relation around these bile nodes while preserving its singular gap nature of the bath. So in particular, we can study how does the bound state confinement change as we tailor the on-site energy offset M. So for instance, when M is equal 1, the isotropy observed for M equals 0 is slightly lost. And in contrast to the previous case, we have two different power law coesystems within the same configuration. Or when M is equal to, for instance, the photonic component of the bound state gets confined along the set directions, leading to a power law which goes as d to the minus 3 along this particular axis, while it spreads over the SY plane, featuring a power law which goes as d to the minus 3 halves. So the possibility of obtaining different power law decays in the same photonic platform by simply tuning one of its intrinsic parameters does not have, up to our knowledge, any counterpart in any other photonic scenario. And here it's important to remark that this power law tunability is ultimately related to the topological protection of the bile points. Okay, so since the single emitter problem has been reasonably understood, we are now in position to explore the two emitter case. And well, in this particular case, we consider the initial state of the system to be the one in which one of the emitter is in its initially excited state, while the other remains in its ground state, and there's no photons in the bath. So we assume that both emitters are equally detuned, and we also restrict ourselves to spatial configurations wherein the two emitters are coupled to sites belonging to the same sublattice and aligned along this set direction. Then, using kind of a two emitters version of this resolvent operator method, we can compute the site state population of both the initially excited and initially de-excited emitter. So that's what we do here for the special case of where no energy offset is considered and the interemitter distance is given by the lattice parameter. So as you can see, we find an oscillatory behavior for both the population of the initially excited and initially excited emitter. But importantly, these oscillations are not complete, but instead they feature well, the maximal value coincides with the stationary state population of the emitter found in the single emitter case. Okay, also in order to demonstrate the long range character of the interaction, we can study the dependence of the exchange frequency of these oscillations as a function of the distance, so the separation between emitters. And well, in particular, when plotting that in this dependence in a log-log scale, we found that it features the same power law observed when studying the bound state profile emerging within the single emitter case. So this observation, together with the fact that the observed oscillations are not complete, indicates that the bound state emerging around the emitter when it is attuned towards the Weyl frequency is actually mediating the interaction when more than one emitter is coupled to the bath. Okay, so moreover, the tunability provided by the topological protection of the Weyl point allow us to explore how this interaction changes as we consider different values for the sublattice energy offset. We found that for this spatial configuration, we can recover for every value of M the same power law behavior than observed within the single emitter analysis. Okay, so with that, I just come to the end of my talk. I just want to say some take-home messages. First, variant environments can actually support the formation of photon-atom bound states that are somehow special because they feature a power law confinement, which is something that is not quite usual in other photonic environments. That when two emitters are coupled to the bath, we observe long-range tunable interactions that are mediated by this photon-atom bound state, and on the top of that, the tunability, observed tunability is actually provided by the topological protection of these Weyl points. Okay, so thank you for your attention. If there is any question, I will be glad to answer it.
Yes, thanks, Inaki, for the quite punctual timing of your talk. So if there are any questions, so there is a question from Alberto. You consider 3D photonic system, but if you would consider 2D system with a synthetic dimension to realize the 3D Weyl points?
I mean, he's talking about considering less dimensions, like to the system with. I guess that if you have 3 dimensions, even if one of them is synthetic, you can still have kind of the same phenomenology, since you have the dispersion relation is quadratic instead of being linear as in Dirac systems. So I guess there's no problem in doing that. I don't know if I have answered the question.
Alberto? He says, okay, thanks. So I also have the question whether, so how much playground you have with the dispersion relation? You have shown that you could shift around the Weyl cones.
Mm-hmm.
Can you induce like pseudomagnetic fields, or can you do like nodal loops?
Yeah, well, we actually just restrict ourselves to changing some particular parameter, which is this, I mean, this on-site energy offset, right? The bath. But well, you can actually, with this particular configuration, you can also add, for instance, staggered hoppings, which leads you to a much more rich change of the dispersion relation around these Weyl nodes. So I guess that as long as you maintain this singular pseudo gap nature of the bath, you can try to do everything to the system that you will still have this kind of phenomenology.
Okay, there is one more question from Henning. Are there any signatures on the QM optical level, like quantum noise, superradiance?
Yeah, we have not. We have actually focused to the emitter being coupled. I mean, to the Weyl frequency. But for instance, for superradiance, you can also try to detune the emitter towards these Van Hoff singularities that appears in the density of states, and by doing so, you can find also important, remarkably non-Markovian behavior, superradiance and so on. So, yeah, I mean, we have actually focused on this particular regime and focus on the emergence of this photon-atom bound state, but you can explore other regimes of the detuning of your emitters, and you will find these kind of things. Yeah, sure.
Thank you, Henning. Is it okay? He says good, thanks. Okay, are there any more questions? If there are, then please say. We still have like 2 minutes until officially the next talker. So if there are no questions from the audience, then I would like to thank Iñaki again for the nice talk, and we can move on to George Frank, who is going to tell us about topological protected ground state degeneracies in interacting two-spin systems. Okay.
Okay, can you see my screen?
Yes, and
my mouse, everything
yes.
works?
Yes.
Okay, thank you for that. Can I start the speech?
Yes, you can start the speech, and your 20 minutes start now.
Okay, my name is George Frank, and I'm a PhD student at the department Budapest University of Technology and Economics. And the title of my talk is Topologically Protected Ground State Degeneracies in an Interacting Two-Spin System. So these magnetic degeneracies are motivated by this experimental setup shown in this figure, where there is a double quantum dot system in a semiconducting nanowire shown in this dark gray rod. We can create this double quantum dot with a double potential well, and these can trap electrons in them, so the electrons cannot move, but they can tunnel to each other, so the electrons feeling each other, so there is interaction between them, and this interaction has a spin signature, so the spin is important. And in the low energy regime of the system, there is only spin degrees of freedom, and there is also an external magnetic field. So we have an Zeeman term in the Hamiltonian in the system, and in the experiment we measure ground state excitations with conductance measurements with these large metallic leads. And in these measurements, we have seen that there are some special magnetic field values where the ground state of this two-spin system has degeneracy, the two-fold degeneracy. And this finding is in good agreement with the von Neumann-Wigner theorem, which states that for a quantum system to have an accidental degeneracy between levels, we have to tune 3 parameters. The 3 parameters now are the magnetic field values, the 3 Cartesian components of the magnetic field. And this is very similar to the wave semi-metals, where there are some band touching points in the quasi-momentum parameter space, but there are some differences and also similarities. So I list here the similarities and the differences. So for the wave semi-metal, the parameter space is the momentum space, the virulence zone, and it has a torus topology. It is a 3-dimensional torus because of the periodic boundary conditions. And the degenerate levels are the valence and the conductance bands. And if we fine-tune the K value, we can find these points. So in this figure below, one case is shown. The arrows are the Berry curvature vectors, and we have 2 points. One is a source of the Berry curvature. The arrows pointing outwards of the red hedgehog, and it has a topological charge +1. The other is blue, and it has -1 charge. Here the vectors pointing inwards, so it is a brane of Berry curvature. And in these systems, we can define a total charge, which is the sum of the topological charges of the points, and it is 0 because the parameter space is a torus. That means that the level crossings are not guaranteed. The von Neumann-Wigner theorem not guaranteeing degeneracies. We can imagine that if we tune a force parameter in the system, these points start to move. They cannot disappear because they are protected by their topological charge. But after some finite perturbation, they can approach each other, they merge, and if they merge, the charge of this new point is 0, then it is not protected, so it can disappear. So it can be, in this phase, the wet semi-metal goes into just a insulator phase. And there can be lattice symmetries or time reversal symmetry or particle hole symmetry in these systems, and this can make restrictions of the points, and there can be symmetries in the prevalent zone of the points. It can be important, and also these symmetries can stabilize degeneracy points along curves or surfaces. So these are called the nodal line or the nodal surface semi-metals. And this was the semi-metals. And for the magnetic degeneracies, the parameter space is the magnetic field values. So it is a three-dimensional Euclidean space. And I investigate here the degeneracy of the ground state. For the two-spin system, the total charge is +2, so it can be non-zero, which means that there have to be ground state degeneracies somewhere in the parameter space, because degeneracy is carrying the topological charge. And here, point group symmetries can be also important, but I will investigate systems without point group symmetries. Only I have time reversal symmetry in the system, which makes it symmetric to the origin, the degeneracy pattern. So in this example shown here, there are two red hedgehogs, and both of them has +1 charge. They are symmetric to the origin. So the total charge is +2 here indeed. And the most simple spin system is isotropic. It has two terms in the Hamiltonian. One is the spins coupled to the external magnetic field. This is the Zeeman term, the first term here. And the second term is the coupling between the spins. And in an isotropic system, there is only scalar products, and it behaves in every direction the same. So if we choose one direction and plot the spectrum, the energies of the states with respect to the absolute value of the magnetic field, we will see one singlet state and three triplet states. The singlet state energy is constant with respect to the magnetic field, but the triplet states are splitting. One is going down as we increase the magnetic field. So at some point, the singlet and triplet states are degenerate. So the ground state is degenerate too. And this degeneracy, if we plot in the three-dimensional magnetic parameter space, it will form a surface of the sphere because the isotropy. But if we want to describe our system, the double quantum dot, there are no symmetries, and there is also spin-orbit coupling, so we can use a more complicated Hamiltonian, where instead of the simple scalar products, there is a linear connection between the spin and magnetic field with the so-called G tensors. These G tensors are real value 3x3 matrices. I assume that the determinant is positive for both of the spins, and also in the interaction there is some matrix. These R matrix is a rotational matrix, and what these terms mean for the G tensors, the meaning is such that in a spin-orbit coupled system, the Kramer pairs have also orbital momentum in the spin momentum together. And for the interaction, the rotation describes a kinetic exchange process when the electron is tunneling between the two leads while it is rotating. And this interaction has J strength, which is positive, which describes an antiferromagnetic interaction. So the spins try to align in opposite direction. And if we plot the spectrum again in some direction with respect to the absolute value of the magnetic field, we will see some anti-crossing generally. But we know that in the system, the topological charge is +2. So it has to have degeneracy point, ground state degeneracies. So the question is, what is the geometry of the degeneracy points? And we can also ask questions, what is the total classification of these geometries? And the answer is really interesting. So we can have 6 different geometries. We can have discrete points, and also we can have ellipses, or in some case, an ellipsoid. Here, there are some ambiguity. How can we distribute the topological charge? So I marked with different colors the different charges. If we have 2 points, it is simple. The 2 points has +1 charge each. But if we can have 6 points, the 6-point case is so that 2 point pairs have +1 charge. Here in the case 4, and 1 point pair has -1 charge. Also, we have 4-point case. In this case, we have 2 points, a point pair with +1 charge, and 1 point pair with 0 charge. And it is not protected by degeneracy, so it can disappear immediately if it were to the system. We have also ellipses. One ellipse has +2 charge because there is no other degeneracy in the parameter space, so the ellipse have to carry this total charge. Also for the ellipse, it has to be charged. And this third case is just the case of the degeneracy sphere for isotropic systems, but here there is no symmetries. So it is some fine-tuned case. And the 6th case has neutral ellipse and point pair. It is very interesting. And in the measurement, yes, and this classification is really just the classification of the eigenvector patterns of 3x3 real valued matrix, non-symmetric matrix. It is important. And it is because we can introduce effective magnetic fields, and these effective magnetic fields have to be parallel. They have to point in the same direction, so it cannot be opposite. So the direction is given by eigenvectors of 3x3 real matrix corresponding to positive eigenvalue. And if it happens, this condition is true, we get crossing. If it is not, we get an anti-crossing. And experiments reveal this interesting behavior. So if we have a measurement in generic direction, the magnetic field is the x-axis, and the energy is plotted here. We have a avoided crossing, and if we tune the system in a special direction, we will get some ground state degeneracy, and in the conductance measurement, we will get a zero bias peak. It is a zero energy excitation. So this yellow blob here is the signature of some degeneracy. And we measured the excitations in every direction, and we get the 2-point case, so where there is only 2 band nodes in the parameter space. And we get this because it is a stable configuration. We have 2 stable configurations, this 2-point case shown, and also the 6-point case. But if we try to, generate random parameters, we will get the 2-point case 89% of the cases. So here the stable patterns mean that we can have these patterns with random parameters with a higher than 0 probability. And there are cases which requires fine-tuning, and one fine-tuning is in this picture plotted here. So if we are in the parameter space of the 2-point case and also in the 6-point case, and we interpolate between them. So here the angle of rotation is plotted for the interaction. So somehow we tune the gate barriers, and for the spin orbit interaction, the angle of rotation can change. And if it is in a specific value, the two point pairs will meet and collide and annihilate each other. And the exact point where they annihilate each other, we get the 4-point case. And we can describe the unstability of such geometries as how many parameters we have to fine-tune for being that the given geometry. So for the 4-point case, we know that only one parameter has to be fine-tuned, the angle of rotation, and these called the codimensions are plotted here. So for the 2-point and the 6-point case, we don't have to fine-tune parameters. The codimension is 0. For the 4-point case, the codimension is 1. And for the ellipses and ellipsoids,
5 more minutes left.
Okay, this is the end of my talk, actually. So these are really high. So for the ellipsoid, it is codimension 8. The more, the bigger the codimension is, the more unstable the pattern. So if we have an ellipsoid and if we just tune one parameter of one G tensor out of the 9, we have to fix the other 8 to have ellipsoid pattern. So this was my end of my talk. So let me summarize the results. So these spin systems, there are topologically protected ground state degeneracies because there is a non-zero total charge. And actually in these two spin systems, we can find and characterize all of the possible geometries analytically. And these analyses reveals rich geometric patterns. And for further investigation, it would be interesting to measure experimentally these other patterns. We only measure the 2-point case. And for further research in theory, the symmetry analysis is an interesting way because with symmetries, the codimensions can change. So we can stabilize these special patterns. So maybe it helps to the experiments to measure some interesting patterns. And for further research, full classifications of larger systems which are containing more spins or larger spins are also interesting. So thank you for your attention.
Okay, thank you for the nice presentation. So now we have a couple of minutes for questions. So if anyone has a question, then please, they should write. I have only one question. Oh, Henning already wrote. So I'm going to ask Henning a question first. How do the degenerative charge in a dissipating system describe a non-Hermitian Hamiltonian?
So here the Hamiltonian is Hermitian. Only I didn't say that for the direction dependence, I have this composite matrix of the G tensors and the R rotation. So this matrix describes the degeneracy directions. So it is not the Hamiltonian is non-Hermitian, but this matrix is non-Hermitian. And if the G tensors are not symmetric, the Hamiltonian is still Hermitian. So there is no non-Hermitianity involved here. Just only the mathematical analog for the direction dependence. Does that satisfy the question?
My question would relate to the fact that you characterized these not point-like degeneracies also with a topological charge, and how can you do that?
Yes, I told about the full charge of such a degeneracy manifold. So if I surround it with a surface, I calculate the chair number, and it will be plus 2 for example the charged ellipse. So it is a question how this charge is distributed on the ellipse. And yes, actually the question is that it is on 2 points of the ellipse. But for ellipsoid, it is interesting that there is a non-zero surface charge density. So for the case of ellipsoid, the charge is not concentrated on 2 points of the ellipsoid. It is different than the ellipse case.
Okay, thank you. If there are no more questions, then I think thanks again for your nice talk, and we can move on. So to the next speaker. And the next speaker is Inigo Robero. Please, Inigo.
Hi.
Hi. Can you share your screen?
Yeah, I'm just a moment.
So Inigo is going to talk about Weil fermions, fermiarcs, and minority spin carriers in ferromagnetic cobalt.
Okay. Can you see the presentation?
US2. Not yet.
Okay. Why not? What about now?
Still nothing.
Okay, I don't know why.
Can you put first the full screen mode and then try to share?
Yeah, I did that.
Then doing the reverse of that.
Okay. So what about now?
Not yet.
It worked well in the. Okay, maybe if I share my whole screen, do you see now?
It says that we are seeing it, but we don't see it.
Wow.
Yeah, it seems that you are sharing something, but we are not. Maybe it's. Are you using a PDF or?
Yeah.
Which
so,
system?
So yeah, I have a PDF. So I've tried sharing just the window where I have the presentation, and also sharing my whole desktop.
Or maybe you can open with a. So are you using a browser for the talk?
No, I'm using the client.
All right.
So still nothing.
So
when you share the screen, you have the option to choose which screen you or which.
Yeah.
So that is not working. Can you open the PDF with another PDF viewer or something like this?
I can try that.
Usually Acrobat or
No, I don't have. So I'm on Linux right now.
Okay. So maybe there is an option of giving some access to the program.
I don't know. But it worked fine the other day, so I don't understand why.
Yeah.
But we can.
Now it's okay. Okay. Now it's getting better. It's still a bit.
Yeah, there is low resolution, but I think we can.
Yeah, it's getting better.
Okay, so then that's
yeah.
Maybe that's because of my Wi-Fi connection. Sorry.
Okay.
No, that's fine. So now could you put in the full screen mode now?
Yeah. How about that?
Yeah.
And close the chat. Perfect now.
Okay. Now we can start.
Thank you.
Okay, let's hope it works. Sorry. Thank you.
Okay.
So, hello. I'm Inigo Robredo, and I'm here to present you our work on Weyl fermions, Fermi arcs, and minority spin carriers in ferromagnetic cobalt disulfide. So first, a little outline of the talk. So first, I'm going to be discussing the material structure and also a little bit of the theory of the topology we can find on this material. Also a little bit of the history, since this is an all-known material for people in the community. Then I will move on to discuss the electronic properties of this system, both the all-known and the comparison to our new RPES experiments, our new high-resolution RPES experiments. Then I will move on to discuss the topological properties we actually found on this material, and just finish the talk with some conclusions and greetings to all my nice collaborators. So this is cobalt disulfide. This is a ferromagnetic pyrite. So this is a really well-known material and has been intensively studied for a lot of years, almost, well, I think decades now. So this was one of the first candidates of being a half metal, so that all the electrons below the Fermi level were spin polarized. And it's also really interesting because of its itinerant ferromagnetism. So in terms of symmetries, this is the crystal is in the non-symmetric space group, Pa3 bar, that when magnetism is taken into account, it subduces to the P prime C prime A, so thus lowering the symmetries. So as I said, we revisited the electronic structure of this material with new high resolution RPES and found a lot of new topological interesting properties that so far have been not seen in this material. So a little bit of an introduction, like, well, a lot of people today, a lot of my colleagues have discussed these things, but let's just make a quick review of the new topological properties we found on this material. So first of all, this pyrite is a magnetic enforced semi-metal. This means that the degeneracies near or close to the Fermi level are symmetry enforced or symmetry protected. So that means that one could not gap the system without breaking the symmetries. Also, due to the time reversal breaking, even though it still preserves inversion symmetry with the magnetism, it breaks time reversal. So we could expect to have some Weyl points, and this is a general feature of ferromagnetisms because of the splitting of the spin up and spin down bands. A lot of crossings can happen, and in general there can be some Weyl points. So the idea of the Weyl points is that they come by pairs. They have opposite topological charge because unlike the previous talk, we are now on a torus. So our parameter space is a torus, so the total charge has to be 0 all the time. So the main signature of these Weyl crossings is that when you go to a surface where the Weyl points are projected onto the surface, then one can see an electronic state that stems from one of the Weyl points onto another one with opposite charge, and this is because of the Berry curvature flow. And so this is one of the properties that we find in the material that I'll discuss later. And then the other thing are nodal lines. So if Weyl points are 0-dimensional crossings, nodal lines would be the 1-dimensional analogs. So the idea is that while Weyl points are only, so they only need the topological protection, for the nodal lines, you need some mirror or glide symmetry that protects the crossing all along the plane. So the idea is that, as you can see here in this little scheme, you have two bands, like they can be parabolic or whatever shape, that cross between each other along a whole plane that's giving rise to this line of connected nodes. So the topological signature of the nodal lines are, so as in the Weyl case, we have one state that connected the two vials. Here we have a collection of states that connect the projection of the nodal line in the surface. So let's move on to our work on this material. So first of all, we did the ab initio band structure calculation. So we can see here that we did the calculation following the usual two schemes, which could be the LSDA, the local spin density approximation, and the generalized gradient approximation for the exchange correlation potential. So as you can see, the bands are really not that different. So the majority, which is the spin up part, is basically the same in both cases. But the only difference is that, as you can see both in the density of states or even just in the band plots, is that in the LSDA case, we have a minority pocket just located at R, while on the GGA we do not have. So this is why historically up to now, people have believed that this material could be a half metal, at least in the bulk, and let's say regardless of the surface effects. Because in general, the GGA calculations are a lot better than LSDA. So as in the GGA, we can see that there's no pocket, and that's why it was believed. However, when we compare to the RPES measurements, we can see that there's actually a pocket at R that can only be explained with our ab initio calculations in the LSDA approximation, where we have this pocket. And so we tried also adding the Hubbard-U parameter to the ab initio calculations, and in both cases, we were not able to reproduce this pocket. So then the conclusion here is that this material cannot be a half metal, because that pocket there has to be a minority spin pocket from our ab initio calculations, thus settling the long-standing question on the half metallicity of cobalt disulfide. So another important feature I would like to remark here is the resemblance of the RPES experiment to our band. So the parabolic band down at R in this direction is really well reproduced. That's giving us confidence that the electronic description that we do theoretically of this system is really accurate to experiment. Then again, we can still compare because we have more RPES measurements, and here we can see that so let's say when you cleavage the material in the 100 direction and measure the Fermi surface at kx equals 0 plane, we can see a squarish shape enclosing the gamma point that is actually very well reproduced in the ab initio calculations here in the right. So finally, this is the last piece of bulk RPES that we computed. So we can see here how the band structure is also well reproduced in our ab initio calculations, and actually we can see here the topological properties that I was talking about a little bit before. So we see here that there's the line node, so just one cut of the line node here near the Fermi level at around 0.2 electron volts below, and also we can see the two bands belonging to the bile cone. So we don't see here the degeneracy because actually the degeneracy is a little bit farther, but still we can see the classical hyperbolic dispersion of these two bands just in the neighborhood of the bile cone. So with this, we move on to the topological properties that we found on this material. So as I said, we found both nodal lines and bile points, and I'll discuss now the nodal lines we find. So even though the magnetism predicts a lot of symmetries on the system, there's still a glide that still lives. That's the MZ 1/2 that can protect nodal lines in kz equals 0 and kz equal pi. So in this case, these are the two nodal lines we find. Well, take notice that they are actually a little bit complex, so they are not strictly closed. They are connected to the boundary turbulence zone because of the non-symmetric symmetries. So we could expect some complex or at least exotic topological behavior of these nodal lines. So to actually check what's the topology, so what are the areas or the regions of the Brillouin that are topological and which of them are trivial, we computed the Berry phases on different points of the Brillouin and actually along different paths, which is basically called the Wilson loop. So because of the mirror symmetry, the Berry phase is quantized to be 0 or pi, basically signaling us that the 0 would be the topologically trivial phase or the topological trivial region, and pi being the topological non-trivial one. So as we can see here, we computed the Berry phase along this green path here, and we see how outside of the projection of the two nodal lines, the Berry phase is 0. That's signaling that this is a trivial phase. While when one gets into the projection of one of the nodal lines, but not the other, we get a pi. That's signaling that in that region of momentum space, we could expect some surface states stemming from them, like the usual drumhead states in the surface. However, when we get into the projection of both nodal lines, we get again a 0. This is because the two nodal lines are contributing each pi to the Berry phase. So basically, pi plus pi is 2 pi, which is the same as 0. In a physical sense, this means that the actual topological states that would live in the surface that are pinned there because of the mirror symmetry can be taken into the bulk without breaking that symmetry. So basically, they kind of annihilate each other. We can see here the Wilson loop on another line, just confirming our prediction that the inside of the nodal lines is topological, while the superposition and the outside is trivial. So now let's move on to the other topological feature we found on this material, which are the bile nodes that are really close to the Fermi level, around 0.1 electron volts in our ab initio calculations. So what we did here is to compute a certain number of the biles by enclosing the degeneracy point in momentum space with a sphere and computing the flux of Berry curvature outside of the sphere. So in here we can see that since the winding of this bile point is upwards, then the charge of this point is +1. So basically we did this for all the bile points that we found because they are related by symmetry. And we found that there are actually 8, a total of 8 bile points in this system. This is a plot of the Brillouin. So the red ones are the ones that have topological charge +1, and the blue ones are the ones that have topological charge -1. So one can expect that when going to a surface, there will be these electronic states connecting the projection of the bile points with opposite chirality that we discussed before. This is what are called the Fermi arcs, as you probably may know. So we can see here in the upper plot, in the upper right plot, that there is a Fermi arc connecting the projection of the red and the blue one here, really in the surface, while a little bit so farther to the right in the middle, we can see that there's the projection of 2 bile nodes that have the same chirality onto the same spot. So if with one bile node we expect 1 Fermi arc, then with 2 bile nodes of the same chirality, we would expect 2 Fermi arcs. And this is indeed what we see. This kind of circular Fermi surface here actually are really the collection of 2 different Fermi arcs that connect them both. As could be expected, because these bands come from really spin polarized electrons, then we could expect that the Fermi arcs to be spin polarized too, but it shouldn't have to be the case. But actually we checked that this is indeed the case. First, we have Fermi arcs that are really spin polarized into the majority spin. So if we would want to use this material as a junction or as a spin injector or just some of these these spintronic devices.
5 more minutes left.
Thank you. Then these surface states would help the polarization of the electron beam. And just in the piece of RPS that you see below, you see this circular Fermi surface that could be misinterpreted as a trivial. Actually, the collection of we believe that is the collection of the 2 Fermi arcs that we see up here. We also see the Fermi arcs when plotting the RPS bands into this direction here, into the gamma X direction, as is signaled here. And we see how in the RPS case, the biles are expected to be just a little bit above the Fermi level. So when going into the surface, we can see the Fermi arc that stems from one of the biles and goes into the other, as in the ab initio plot here in the right. So let me finish with some conclusions. So what we did with this material is to settle the long-standing debate on whether this cobalt disulfide pyrite can be a half metal or not, and we see that it cannot because of this minority spin pocket that probably can be removed with just a little bit of doping. But it is not in its actual natural form, let's say. And we also found new topological properties on this material that have eluded the studies so far. Thus, bringing up the idea that even old materials or materials that have been with us for decades now can display some exotic new behavior that we did not they showed because of maybe the physics didn't exist at that point. So let me quickly wrap this up by thanking my collaborators. So on the experimental part, I have Leslie Scoop from Princeton and her lab, and Niels Schroeder and their collaborators from the Paul-Scherrer Institute for growing the material, cleavaging it, and doing this beautiful RPS that we have. And on the theory part, I would like to thank Fernando de Juan and both my thesis supervisors that are Maya Garcia Berniori and Naitor Perra. And with this, I finish. Thank you.
Thank you for the nice talk, Inigo. So we have time for one question. So if anyone has a question from Albert, so Albert has a question. Did you mention that cobalt disulfide is magnetic material?
Yes.
Yes, I think so. It was the first half of the talk.
Yeah. It's a ferromagnet.
Yeah. Yeah, so I think we have one more question. Yeah. So if there is no question written by the okay. Then, so what do you expect in terms of the anomalous Hall signal? Is a question from Alberto.
Yeah. So yeah, that's a nice question. So as in. So the idea that in general that bile semimetals would have a large anomalous Hall comes from the idea that the very curvature diverges around the bile nodes, right? But the thing is that the area in which the very curvature diverges it's actually 0-dimensional because it's just the bile. So in general, I could say that we should not expect much of so let's say that we shouldn't expect a large anomalous Hall because of the biles. It might have because of the other bands that are lying around the Fermi level.
So
I don't know if that's satisfying enough.
Well, maybe I can switch on the microphone. Well, my question was more related to what is the behavior of the nodal line with respect to the anomalous Hall signal? Do you expect Hall signal, not for the biles, but for the nodal line somehow, something like this? Sorry.
Yeah, so I'm actually not sure about the nodal line in general, but in this material, I can tell you that the nodal line is a little bit down in energy, so around 0.2 or 0.3 electron volts. So probably it shouldn't contribute much to the anomalous Hall. But as a general question, I actually have no idea, but I think it's really interesting.
Okay, thank you again, Iñaki, for the nice talk, and I think we are reaching to our. So we started with a Balázs, and I think we can also finish with a Balázs in this section. So I asked Balázs Gulácsi to give his presentation. So if Balázs, could you share your screen and also unmute yourself? Okay.
Hello, can you hear me now?
Yes, we are still having problems with your screen.
Okay, I didn't share it yet, so let me
share your screen. You can also share your video feed so that we know how you look.
Now, can you see the?
Yes, your slides we can see. Can you also share
Okay,
your?
and I switch on the
camera.
If I find it. Okay. Now, hello everyone.
Yeah. Okay.
Okay, so now you see my presentation.
Yes.
And
so,
if I make it to full size, you can see it as well. Okay, full screen mode.
Yes. Yes.
Okay.
So
now.
Okay, you have 20 minutes. Okay.
Yes, thank you. I'm grateful for the opportunity to speak here about my work. My name is Balázs Gulácsi. I work in Budapest in the University of Technology with Balázs Dóra. We had the pleasure of hearing about his work in the morning earlier. And now I will talk about our recent work with geometrical quench and dynamical quantum phase transitions in the alpha T3 lattice. Now I will start with a very brief introduction into dynamical quantum phase transitions. It is a relatively new topic, and it is very vast, so I won't go into detail. I will only talk about just the main points that is necessary for us to understand the results of our work. So let's start with conventional phase transitions. So physical system can be in very different states. These states have very different macroscopical properties. This is what we call phases, and we can actually make a system go from one phase into another by changing a control parameter, for example, temperature. Now, if we theoretically want to describe this, what we do is use statistical physics. We use a partition function. From that, we calculate the energy density. And what we can see is that the free energy density or another thermodynamical potential will depend on the control parameter. And we will see that during a phase transition, this function will behave non-analytically at the critical value of this control parameter where the phase transition occurs. So for example, if you see melting, when ice becomes water, we know that the volume of the matter changes. So that means that the first derivative of the potential will have a jump or a discontinuity, or it is in the potential, it will have a kink. So if we have this function, which is the potential, it is a function of an external parameter, it will have a breaking at the at some point. So that is a kink. Okay, and that point there is the phase transition. Now I put here superconductivity here as well because you know that at the critical temperature, the heat capacity has also a discontinuity. Now let's move to the non-equilibrium part of this talk. So there are plenty of interesting non-equilibrium phenomena involving quantum systems, closed quantum systems, and the development of experimental techniques actually make it possible to experimentally study the real-time evolution or the real-time dynamics of closed systems. Now, a closed system can be described with a Hamiltonian, and this Hamiltonian also governs the time evolution through the Schrödinger equation. Now, a Hamiltonian can be dependent on an external parameter. So we can drive a system out of equilibrium by changing this parameter to another value. So if we have a Hamiltonian, the system, and we prepare the system in an initial state that is the ground state of this Hamiltonian, this psi 0, with psi null, then we change the parameter in the Hamiltonian, then the time evolution won't be trivial. So the time evolution for this initial state with the initial Hamiltonian will be trivial because it only picks up a phase. But if you change the parameter suddenly, then a new Hamiltonian will govern the time evolution, so it won't be trivial anymore. And we can study the reaction of the system so the reaction of the system of this change, this sudden quench. And one way to study this dynamics is to study the return amplitude or the Lock-Schmidt amplitude, which is the inner product of the initial state and the time evolved state. The absolute square of this value is the Lock-Schmidt echo, which is the probability that the system will return into the initial state. Now, if we write it out, we can see that this is actually the expectation value of the unitary time evolution operator in the initial state, and this is very similar to the partition function. And this is a formal similarity that births the whole theory of this dynamical quantum phase transitions. So in this, we can use, instead of the partition function, this return amplitude or the Lock-Schmidt amplitude, and we can define free energy density-like expression, which is the dynamical free energy density, or in other words, the rate function. So this G is actually depends on the system size, and it decays exponentially, and it depends on the rate function as well. So if you work it out, we get this expression, so the sixth expression, which is a logarithm of the rate function. And this is very similar to the free energy. So this is the dynamical counterpart of the free energy density. And I talked about that in a conventional phase transition. The important thing is that during a phase transition, the potential behaves non-analytically at the critical value. And that shows you the phase transition. Now we can define a dynamical quantum phase transition by the non-analytic behavior as a function of time in this dynamical free energy density. Okay, so this is what is important here, that this is the definition of the phase transition. Now there are plenty of systems that can exhibit this kind of phenomena. I will show you only two now, just so you can get a feeling of this. The first is the very first of this, so the one-dimensional transverse easing model. So when the concept of these dynamical phase transitions were made out, in that paper, the actual model that was studied was this one. Now this is a simple spin model, one-dimensional. It has a parameter, the G, which is the applied field strength. What is important here is that this model has a quantum phase transition. So it has a critical coupling strength G, where the ground state of the Hamiltonian changes. So below this critical value, the ground state is a ferromagnetic one, and above this value, the ground state is a paramagnetic one. And if you change during a quench, if you prepare the system in an initial ferromagnetic state and you quench the control parameter above the critical value, that will guarantee you a dynamical quantum phase transition. So this model can be realized in ultra cold setting, in an ultra cold trapping environment. This can be seen in the first graph here. In the first graph, what we can see is the rate function. So the rate function is the dynamical counterpart of the free energy. And what you can see here is a solid line, which is a calculated one. And there are these dots, which is the measured. So these results from the measurements. And this is now I tell you that it can be realized, this one-dimensional transverse Ising model in a trapped, ultra-cold trapped environment. You trap atoms and the interaction between them can be modeled by this effective Hamiltonian. And you can measure the rate function. And what you can see is that at critical times, you have those kinks in the rate function itself. And if you think about it, that you prepared your system in a ferromagnetic phase and during a phase transition where the non-analyticity happens, we see that the rate function is actually a logarithm of the return amplitude. It can be non-analytic whenever the return amplitude will be 0. Now the return amplitude we know is that the probability that the system will go back into the initial state. And we know that the initial state is a ferromagnetic one. So it has a non-zero magnetization. But the probability of going back there is 0. So now if we measure magnetization, we have to get 0 at the critical times. And this is what is shown here. So these are the kinks that corresponds to the dynamical quantum phase transition. And the consequence of this is that here the magnetization has to be 0. Okay, so this is how a rate function with the kinks looks like. Another important thing is the dynamical topological order parameter. So for this kind of phase transitions, we can define an order parameter in a sense that it is a quantity that will change value whenever a phase transition occurs. And it is topological in the sense that it is an integer. So whenever a phase transition occurs, this integer will change value. Now, to tell you an example about this, let's see a simple lattice model. So if we have a lattice model, then the crystal momentum is a good quantum number for it. And that means that the Hamiltonian can be written as a sum of different Hamiltonians that depend on the momentum. Now it will result in that the return amplitude also factorizes, so it will become a product of different return amplitudes that depend on the momentum. Now, so we saw that the phase transition happens at times whenever this G is 0. Now this is a product, so whenever there is a K momentum where this return amplitude is 0, then the whole product will be 0. So it is enough to study this quantity here. So whenever there is a K where this return amplitude is 0, then there will be a phase transition, to a dynamical phase transition. Now in general, the return amplitude is a complex number. So it has a real and imaginary part. It can be written in this way. So it has an absolute value and a phase. Now, if we think about it, if we study a two-band system, it can be considered as a system with two states. It can be described on a Bloch sphere. So if you're not familiar with it, the Bloch sphere is a one radius sphere, and every point on the sphere surface can be understood as a different state of a two-level system. So it can be described with the theta and phi angles. And if you write it down, it can be seen this way. Now, if we do a quench in a way that the initial state is actually the one pointing north, that will be the 0, 1 vector. That means that the return amplitude is actually this quantity. So the phase of the return amplitude is actually the azimuthal angle of the Bloch sphere representation of the two-band model. And that is actually measurable by state tomography techniques. And this was done here. So I told you this because this is how you can see that we can actually define a dynamical topological order parameter. So what you see here is the azimuthal phase in these pictures at different times. So the first one is at time equals 0, and then different times you can see the snapshots of the azimuthal phase. So it is two-dimensional. So I didn't tell you that this experiment was made on a hexagonal lattice in 2 dimensions. The quench was that the hopping between the sublattices were switched off. No, so in the beginning, the initial state is where there can be any tunneling between the sublattices, and they switch on the tunneling and then measure these azimuthal phase graphs. So what you can see here in the first picture is that there are these circles. These denote the static.
I have 5 more minutes.
Oh, okay. Wow. I will move on then. So what is important here is that the order parameter here is the moving vortices. So a vortex is very important. So a vortex is important because it defined as an area where every azimuthal phase can be available, is available. So here, you can find every azimuthal phase. So that is a vortex. And the order parameter is every moving vortex. So we have 4 here, but those are static. So you can see everywhere they are there. But there are 2 others that are moving. So the different times you can see that they are moving here. So the order parameter is the number of these moving vortices. Okay, I talked too much about this. And now let me tell you about the actual work. So what we did, we studied this alpha T3 lattice. This is a 3-atom unit cell. On a triangular lattice, there are 3 atoms, the hub site, which is connected to both other atoms. They are so the red one is connected to the blue one and the triangle one. It has a hopping ratio gamma and gamma prime. Now what I will tell you that the ratio of the 2 will be denoted by alpha. This is a triangular lattice, so it has a Brillouin zone, which is a hexagon. And at the edges of the hexagon, there are Dirac points. And there are, at the Dirac points, the dispersion relation is similar to the graphene, it is linear. But if we put mu chemical potential to the hub site, then there will be a gap in the spectrum, which can be seen here. And so, okay, I don't have much time. I will tell you that the point of this is that what we studied is we prepared the system in a fully filled low energy band with the Hamiltonian parameter mu nil and alpha nil. And the geometrical quench was that we changed these parameters into another. So we changed the size of the gap and the ratio of the hoppings. What we do here is we calculate the return amplitude and see if there are any dynamical quantum phase transitions. Now, I told you that these factorizes. So in principle, this is just 3 complex numbers, and we have to add them up. And we get 0 whenever these complex numbers, as depicted on a plane, form a closed polygon. So you can see here is that this is the red one, the black and blue arrows depict as the complex numbers of this sum. Now, if we add them together, we get 0 whenever they are forming a closed polygon. We know that the occupation numbers will add up to 1, and to form a closed polygon, so the lengths of these arrows are the occupation numbers of the post-quench states. To form a closed polygon, they have to obey a triangle equation. Now combine this with the fact that they add up to 1, we get this condition for the quantum phase transitions to occur. So what we have to do is that there will be a phase transition if there exists a non-zero momentum for which every post-quench occupation is below 1/2. And this is what we study here. So when we see the first quench scenario where we open a gap and change the ratio, these are occupation probabilities. So we can see here that there is a constant one. This is the probability that the particles will be freezed into the flat band, and these are the other two. What we can see here is that every time we do this quench, there will be a momentum. So I didn't tell you that the Hamiltonian is rotationally invariant. So every quantity will be dependent on the magnitude of the momentum. So I can make.
Sorry, Balázs. I think we have to finish because we are out of time. So
okay. So the point here is that we measure. So we calculate the return amplitudes. We get that there is. We get that the rate functions are universal in a sense that there is only one energy scale, the mu, and there are these dynamical quantum phase transitions that occur at these times here, whenever the alphas are different values. Here in this line, there are other phase transitions in the derivative. So this is the graph of the rate function. It has the kinks, it has the non-analyticity. So these are the phase transitions. And in this line, the derivative has the kinks. So there are two types of phase transitions here. And what is important, moreover, is that we worked out that so I talked about these vortices. So here you can also define vortices, and what is important here is that these vortices appear as a macroscopically number. So there are infinitely many vortices that appear here, and at the times of the phase transitions. Yeah, that will be the summary. So when we so this is where. So when the first picture is when we quench from a gap. So when we create a gap, we can see the blue one is where the phase transition occurs on the derivative. This orange one is where the phase transition occurs in the rate function itself. And when we open a gap, when we have already a gap and do this phase transition, there are certain alpha values when there are no phase transitions, and this blue and orange one is the same. So when we have phase transitions in the derivative or in the phase itself. Okay, but thank you very much. I regret it that I didn't manage my time so well. But if you have questions, I can answer.
Okay, so thank you for the nice talk. I mean, some things happen sometimes that you are going over, so don't worry. Yes. But we don't have time now for questions, but there is going to be another session in the afternoon. I just remind everyone, which is going to be where we can look at the posters, and there is going to be also an informal setting for the whole session to get together again and discuss all the previous talks as well. So if people want to ask questions, then everyone is welcome to join there. And Alberto just reminded me that everyone should switch on their video again. So this, I think, also includes all the participants who are joining in, because we want to make a
I should stop sharing now. Right?
Yes, we should stop sharing. Please. And then we should go to, everyone should try to look nice for the screenshots. So please, everyone, if you are here, you should.
So anyone who wants to appear in the screenshot, please turn on the camera. But the point is that apparently the systems only allows me to make 16 pictures, 16 faces pictures. So, well, I'm gonna make one of those who are here with the camera. So anyone who wants to switch on his or her camera, yes, and to smile in the picture.
Please. Yeah. Please, more and more people. So there are still a couple of them here.
Okay, I'm gonna proceed. So see topology, no, say cheese.
Cheers.
Okay, good. So thank you all for being here, and thank you for this meeting. So it was quite good. So I encourage you all to be in the afternoon session. Just I know you want to discuss with today's speakers, or if you want to discuss with anyone else, please join us in the afternoon session.
Yes, thank you again, and see you around. Hopefully next time in real life. So,
okay.
Yeah. Okay.
Fine. Bye. See you later.
Bye.
Bye.
Ciao.
Bye bye.
Bye.